All right, Unit 9, circles, day 2. So today we're going to measure angles and arcs, and then we're also going to look at how we deal with chords. First thing is, hopefully you guys remember that in any circle there are 360 degrees. So if I go all the way around a circle one time, I've gone 360 degrees of rotation. What that means is that if I only know a couple of angles, a couple of central angles within a circle, I can figure out a third one if it's broken into threes. Or if I know 4 out of the 5 angles, I can figure out the fifth one. But in this one right here, basically the circle is broken up into 3 parts. And so I have 3 angles, 3 central angles. This one right here, it's telling me is 90, right? Because the little box there means this angle is 90. This one here is 120. And so we could call this one X. And kind of like when we're solving for a missing angle in a triangle, I can just say that 360 equals 90 plus 120 plus the one I don't know yet. If I add those two together, my equation would be 360 equals 120 plus 90, which is 210 plus X. Subtract 210 from both sides of the equation. And X would end up being 150 degrees. So this right here would be 150 degrees. So again, the idea is that any circle, if you look at the central angles, in other words, angles measured from the center of the circle, they have to add up to 360. All right. So given what I just said, why don't you guys take a couple minutes, so pause the video if you're watching this, and figure out what X would be in each one of these circles. And then once you've figured them out, press play again and I'll go over how to do them. All right, so in the first one, there's really only 2 angles, right? There's this one right here in red, and then there would be this one right here in blue. Those 2 angles together have to add up to 360. So this one is kind of simple. You really don't even need to write an equation for this one, because the way to solve for it is basically just to subtract the angle that I already have from 360. So I start with 360 degrees. 130 of it is taken up by the angle that I know. That leaves 230 for the other one. Okay, on the second example, I have 2 angles here. One that's 270, another one that's 52, and then X. Okay, so for this one, 360 is going to be equal to 270 plus 52 plus the one I don't know yet. 270 and 52 is 322, so 360 equals 322 plus X. If I subtract 322 from both sides, again I'm going to do 360 minus 322. It's going to leave me with 38 degrees, so X would be 38 degrees. Last one here. Again, I only have 2 angles. This one right here is 90. The rest of this whole circle is X. So I'm just going to subtract 90 from 360. And so the rest of this one, in other words, X, would be about 270 degrees. So some more terminology about circles. An arc, A-R-C, is the part of a circle that's created or made by a central angle. So a central angle just means an angle that where the vertex is at the center of the circle, basically. So take a second and pause the video if you need to, and draw these 2 angles, these 2 central angles, into the 2 circles on the left here, the minor arc and the major arc, and then I'll explain what those are. So minor arc is just when I have a central angle like this 95 degrees right here, the minor arc is the smaller of the 2 arcs created by that central angle. So the part of the circle that connects the 2 endpoints of the radii, that's a minor arc. If I have the same central angle, the major arc is the bigger of the 2 arcs created by that central angle. Okay, so a minor arc is the smaller arc created by a central angle. The major arc is the bigger arc created by a central angle. So any angle I have, almost any angle that I have inside of a triangle, or sorry, inside of a circle as the central angle, will have a minor arc and a major arc. The only kind that doesn't is if I have a semicircle, and that means if my central angle is just made by a diameter, right? So there's going to be 180 degrees over here, another 180 degrees over here. If my central angle is exactly 180, then I don't have any minor arcs or major arcs because the two arcs are going to be exactly the same. Right? Both of those arcs are going to cover 180 degrees of rotation. So I can have minor arcs, major arcs, or a semicircle. And the only time you have a semicircle is when your arc is exactly 180 degrees. How do I label arcs? Well, for a minor arc, I just need 2 points, such as A and B. Okay, so minor arcs are labeled with 2 endpoints, and the way I would write that would be AB with an arc over top of it. For a major arc, we have to use 3 endpoints, or 3 points, and here's why. If I just said arc AB, you might think I meant the minor arc on the top of the circle here. If I put another point down here, such as C, and I call this arc ACB, now you know I'm talking about a major arc, because to get from A to C to B, I have to travel along that major arc there. For a semicircle here, I just need 2 points, basically. All right. A to B would be my arc in either case there. All right, measuring arc length. So arc length, it's not difficult. This formula looks more complicated than it really is. So remember, circumference means the measure of the total length all the way around the circle. Okay, but for arc length, what I'm saying is, well, how long is just this part of the circle, right? In this problem, I'm just looking for the length from A to B, basically. And so if the only information I have to start with is the central angle here, which is 105, and then the radius, which is 5, I can figure out how long that arc is. And here's the formula I use to do it. So the length of the arc that I'm looking at is just going to be 2 times pi times the radius, which in this case is 5, times x, which is the central angle. Okay, so I just substituted in a 5 for the radius and a 105 for the central angle. I divide all of that by 360. So on the top, I'm just multiplying 2 times pi times 5 times 105. So let's do that first. 2 times pi times 5 times 105. So I get a big number, 3,298.67. And that's divided by 360. So there's really only one step left. Take what I just found here and divide the whole thing by 360. So the answer here is 9.16. So the length from here to here, if the radius is 5 and the degree over which this arc travels, the central angle over which this arc travels is 105 degrees, the length of this part of the arc, or this part of the circumference really, would be 9.16. All right, well, let's say instead I have the same circle, the same central angle, but now instead of telling me that the radius is 5, it tells me that the diameter is 10. Same procedure really. It's just that now we don't have to do the 2r, we do a d instead. So it's going to be pi times the diameter, which it tells me right here is 10, times x, which is the central angle, all divided by 360. And so if the diameter here is 10, it means the radius is 5. So I should get exactly the same answer as I got before if I'm looking for the arc length of A to B here. And what I got on the last one was 9.16. Yeah. So for this one, I should get about 9.16 if I do this correctly. All right, well, now I just have to multiply pi times 10 times 105 for the top. pi times 10 times 105 equals similar, the same numbers I got before when I multiplied the top, which is what I should get, 3298.67 divided by 360, and that's just going to equal 9.16. Again, if you want me to verify, I will. 9.16. Okay, so the same answer, which is what we should get, because really what we have here is the same information. It was just presented a little bit different. We were given a diameter instead of a radius to start with. So it's up to you. If you feel more comfortable using a radius, do that. If you feel more comfortable using a diameter, just double the radius and use this formula. All right, so what if I want to work, what if I have the central angle and I know the circumference? Right? What if I already know the entire circumference of the circle? I don't know the radius or the diameter, but I know that all the way around the circle, one time, is this 31.4, and I know that the central angle here is 105. Can I figure out from that information how far it is just from A to B? In other words, the measure of arc AB. And of course the answer is yes, you can. I have the formula for it right over here. The length of that arc would just be C, which is circumference. So 31.4 times X, which again is the central angle, so 105, divided by 360. And if we do this correctly, we should get an answer of 9.16 again, but let's check to make sure. So the circumference is 31.4. I'm going to multiply that by 105. And I get 3,297. And that's divided by 360 still, so 9.158, which I would round up to 9.16. Not because I want to cheat, but, well, maybe I want to cheat a little bit. So the length of this arc would be, again, about 9.16. The reason we got 9.158 or something on this one, and we got 9.16 point something on the other, is because of rounding. And so if it was on a test and you got 9.15 something and the closest answer was 9.16, you would go ahead and answer 9.16. All right, the next thing we have are arcs and chords. More specifically, we're going to talk about the relationship between arcs and chords. So again, a chord is a line segment with two endpoints on a circle. So FG is a chord and JH is a chord on both circles. These two circles are the same. I'm going to use them both for different things here in a second. So if I just look at the one on the left, like I said, FG is a chord and JH is a chord. And what you can see is that both of those chords sort of create minor arcs, right? There's a minor arc that connects F to G and a minor arc that connects J to H. One of the rules we have is that if those two chords create minor arcs that are congruent in length, in other words, if minor arc F to G is congruent to minor arc JH, then that means that chord FG is going to be congruent to chord JH. So, and that sort of makes sense, right? If JH and FG, in other words, are both, let's say, 8, then both FG and FG is 9, then JH would also be 9. Okay, so that's one way this works. So two chords that create congruent minor arcs are themselves congruent. And it works the same way in reverse. Two chords that are congruent create congruent minor arcs. So let's say instead I start out knowing that FG is congruent to JH. That tells me then that arc FG is congruent to arc JH. Next thing, if a chord is perpendicular to a radius within a circle, the radius bisects the chord. Okay, let's see what that actually looks like here. So here is XY, it's a chord within circle C. So XY right here is a chord within circle C, and CB is a radius within circle C. What this is saying is that anytime I have a chord that's perpendicular to the radius, that radius CB bisects XY. So let's say that let's say I knew that XY was equal to 8. That means that CB bisects it. In other words, XZ is going to be 4 and ZY would be 4. Or let's say that XY instead is equal to 22. That means I have 11 here and 11 down here. At the same time, if a radius bisects a chord, the radius has to be perpendicular to the chord. So in other words, let's say instead I start out with this information, right? I still have X, Y as a chord within circle C, and I still have CB as a radius within circle C. But let's say I don't know whether those two are perpendicular yet. And then let's say I'm given the information that XZ is 7 and ZY is 7. If this radius bisects this chord, it means that these two have to be perpendicular. If two chords in the same circle are congruent, so let's say that FG and GH are congruent. In other words, let's say FG is 10 and HJ is also 10. If those two chords are congruent, they are the same distance from the center of the circle. Right, so what this is showing here is that I have chord JH, which I said was 10, chord FG, which is 10. What these other lines are showing is that if those two chords are the same length, they have to be the same distance. In other words, these two distances between those chords and L, which is the center of the circle, also have to be the same. So let's just put more numbers in here. I said that this is 10 and this is 10. If that's the case, if I take the shortest distance between that chord and the center of the circle, those two also have to be the same. So let's say that's 6 and that would be 6. By the same token, or kind of the flip side of that is, if I start out knowing that there are these two chords, if I start out knowing that the distance between the center and those two chords is the same, so let's say I know that that's 14 and that's 14. The distance between the center and each chord is 14. That tells me then that the chords have to be the same length. So if these two distances are the same, that means the chords have to be the same length. So something like this. So let's actually do an example of that, and hopefully it'll make more sense. On this example right here, I'm told that these two minor arcs right here, so minor arc AB, minor arc CD, are both 127 degrees. That means that the two chords that sort of created those minor arcs, in this case A to B and C to D, have to be the same as well, right? Chords that create congruent minor arcs are themselves congruent. What that means is that 5x, which is this one, is equal to 3x plus 6. And then I just solve it as I would solve any multi-step equation. I'm going to subtract 3x from both sides. Those go away. 5x minus 3x is 2x equals 6. Divide both sides by 2, and x would be equal to 3. So if I wanted to know the length of the chords, since I know they're the same, I would really only have to substitute in for one of them, right? And I'll just do the 5x. So A to B, chord AB equals 5x. I know that x is 3. So instead of writing 5 times x, I can write 5 times 3, which is 15. So both chord lengths would be 15. Okay, now I have one where the radius is bisecting a chord. So I'm told JK is 10. So the distance from here to here is 10. since I know that this radius is perpendicular to the chord, I know it bisects it, so I know that part's going to be 5 and that part's going to be 5. And then I'm told the measure of arc JLK, so from here to here to here, in other words, this right here, is 134 degrees. And so this distance out here is 134. What it wants me to do is find the measure of JL and then find the length of PQ. So here's what we're going to do. To find JL, what's happening here is basically this chord intercepts 134 total. If that chord is bisected, then that means that this minor arc is also bisected. In other words, this 134 will just be cut in half, right? So half of it's going to go over here, half of it's going to go over here. So 134 divided by 2 is going to be 67. So the measure of minor arc JL is 67. P to Q is a little bit more complicated. So here's Q and here's P, and it wants to know just the distance between those two. So this little distance in here is what it wants to know. To do this one, we're going to have to return to the Pythagorean theorem. So I'm going to draw a little line here. I'm going to use all this space for PQ because I'm going to redraw the circle so that I just have the stuff that I need. Okay, so that's L to M. And then I have J to K right here. Center of the circle is P. I know that this part of the lines, or this line segment right here, is 5. I'm told that the radius from M to P is 6. No, that's 5. So here's what I'm going to do. I know that these two are right angles. So what I'm going to do is I'm going to create a right triangle. Right? The reason why I'm going to do that is because I know that the distance from P out to J is a radius. All radii within the same circle are the same. So if this radius is 6, then this radius would be 6. And now I'm just going to extract, I'm just going to take out this little right triangle right here, and I'm going to redraw it by itself. This side is 5, the hypotenuse is 6, and then this over here is actually PQ. So that side right there, P to Q, this side right here is the one that I don't know yet, and that's what I'm going to solve for using the Pythagorean theorem. First thing I always have to do is figure out which side is C, and C is always the one across from the right angle. So I'm going to have 6 squared by itself on one side equals 5 squared plus x squared. And whatever I determine x to be, that's the length of PQ. So 6 squared is 36, 5 squared is 25. I'm going to subtract 25 from both sides of the equation. 36 minus 25 is 11, so 11 equals x squared. And then to find x, I just have to take the square root of 11. So 3.32, let's say. So the distance from P to Q right here within this circle, or this one right here, would be about 3.32 units. This one says in circle J, GH is 9. So G to H, that part right here, is 9. And it says KL, so that chord right there, K to L, is 4x plus 1. It wants us to find x. Well, the picture's sort of telling me that those two chords are going to be even or equal in length because the distance between the chords in the center of the circle, J, is the same. In other words, G to H is going to be congruent to KL because the two chords represented by these symbols over here are the same distance from the center of the circle. So GH is 9, KL is 4x plus 1. Subtract 1 from both sides, I would get 8 equals 4x. Divide both sides by 4, and x would equal 2. And I believe that's it for day 2.